If a loose connection exists on the breaker causing a poor contact on one phase leg, it's plausible that power could still flow to the range through the other two phases. Upon the range being activated, it may create a conduit for the current to return through the affected phase wire through the range's internal mechanisms. This may unfold in a few steps. Firstly, power extends from the circuit breaker to the range on phases A and B. Secondly, the range consumes power from both phases. Thirdly, current navigates back to the panel via the neutral wire. Fourthly, owing to the compromised connection on the breaker, phase C is not facilitating a viable pathway for current to return. Fifthly, the current originating from phase C courses through the range, subsequently making its way back to the panel through the neutral wire. This effectively energizes the afflicted phase, that is phase C, within the panel, utilizing the range's circuitry. If the unstable connection on the breaker were to intermittently establish a reliable connection while this current persisted in flowing back through phase C, it is a possibility that the main breaker would trip. When the precarious connection is re-established, it may allow the current to circulate through all three phases once again. However, in instances of excessive current draw or circuit overload, the main breaker has the potential to trip to safeguard the circuit. Several factors come into play. Firstly, the size specifications of the range coupled with the magnitude of power it necessitates will bear an influence on whether the main breaker is prompted to trip or not. Secondly, the presence of auxiliary loads in the implicated phase would also influence the likelihood of tripping. Thirdly, the span separating the breaker panel and the range could potentially exert an influence, as more extensive wires exhibit heightened resistance, which can, in turn, modulate current flow. In summation, the scenario wherein power flows to the range across the alternate phases and retrogresses via the afflicted phase through the range's intrinsic circuitry remains a distinct possibility. Furthermore, in occurrences where the circuit undergoes an overload, or the connection and the breaker is momentarily rectified, the culmination might very well manifest in the tripping of the main breaker. Let's delve a little deeper into the workings of an electrical system in a home and how a range interacts with it. Homes typically receive power in a split-phase 240-volt system. This means there are two 120-volt legs, often referred to as phase A and phase B, and a neutral wire. The voltage between phase A and phase B is 240 volts, which is used for high-power appliances like electric ranges, water heaters, and air conditioners. The 120 volts is used for lighting, receptacles, and smaller appliances. The main breaker in the electrical panel protects the entire electrical system from overloads and short circuits. It is sized to handle the total current load of the house. Individual circuits are protected by their own circuit breakers, which are sized to handle the current load of that particular circuit. Now, let's consider the case of an electric range. Ranges typically require a 240 volts power supply, which means they are connected to both phase A and phase B. The range also has a neutral connection, which is used for the 120 volts components of the range, such as the oven light and the electronic controls. When the range is turned on, current flows from the circuit breaker to the range on both phase A and phase B. The range uses this power to heat the elements in the oven and on the stovetop. The current then flows back to the panel through the neutral wire. In the scenario described, there is a loose connection on one of the phase legs of the main breaker, specifically phase C as it was referred to. This loose connection creates a high resistance point in the circuit. When current flows through this high resistance point, it generates heat. This is why the breaker was hot to the touch. The loose connection also disrupts the normal flow of current in the circuit. If phase C is not providing a proper path for current to return, the current from phase C may flow through the range and back to the panel through the neutral wire. This can happen if the range has internal circuitry that connects the neutral wire to the heating elements. In this case, the range is acting as a bridge, allowing current to flow from phase A and phase B through the range and back to the panel through the neutral wire and the affected phase C. This is what is meant by powering the affected phase in the panel through the range's circuitry. Whether or not the main breaker will trip depends on several factors, including the size of the range, the amount of power it draws, and the presence of other loads in the affected phase. If the current draw is excessive, or if the circuit is overloaded, the main breaker could trip to protect the circuit. The distance between the breaker panel and the range can also play a role. Longer wires have higher resistance, which can affect current flow. This resistance can limit the amount of current that can flow through the circuit, which can reduce the likelihood of the main breaker tripping. Now let's talk about some additional safety considerations. Electrical work can be dangerous, and it is important to take precautions to protect yourself from electric shock. Always turn off the power to the circuit before working on it. Use a non-contact voltage tester to verify that the power is off. Wear safety glasses and gloves. If you are not comfortable working on electrical circuits, hire a qualified electrician. In this particular case, it was fortunate that the problem was identified and corrected before it caused a fire or other serious damage. A loose connection in an electrical circuit can create a fire hazard. The heat generated by the loose connection can ignite nearby materials. It is important to inspect electrical panels and circuits regularly for signs of loose connections or other problems. If you notice any problems, have them corrected immediately. One important concept to understand is the difference between series and parallel circuits. In a series circuit, components are connected end to end, so that the current flows through each component in turn. If one component fails, the entire circuit is broken. In a parallel circuit, components are connected side by side, so that the current has multiple paths to flow through. If one component fails, the other components can still function. In the case of the electric range, the heating elements are connected in parallel. This means that if one heating element fails, the other heating elements can still function. However, the total current draw of the range will be reduced. Another important concept to understand is Ohm's law. Ohm's law states that the voltage across a conductor is proportional to the current flowing through it. The constant of proportionality is called the resistance. Ohm's law is expressed by the equation volts equals current times resistance, or volts equals amps times ohms. Ohm's law can be used to calculate the current flowing through a circuit if the voltage and resistance are known. It can also be used to calculate the voltage across a component if the current and resistance are known. Understanding Ohm's law is essential for troubleshooting electrical circuits. Another key factor to consider is the National Electrical Code, or NEC. The NEC is a set of standards for electrical wiring and equipment in the United States. The NEC is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. Electricians are required to follow the NEC when installing electrical wiring and equipment. The NEC is designed to protect people and property from electrical hazards. There are many specific NEC requirements that relate to electric ranges. For example, NEC Section 210.19 A3 requires that the branch circuit conductors supplying a range shall have an ampacity not less than the rating of the range. This means that the wires that supply power to the range must be large enough to handle the current the range draws. NEC Section 220.55 provides rules for calculating the load for ranges. This section takes into account the fact that ranges are not typically used at their maximum power rating for extended periods of time. NEC Section 250.20 B3 requires that the metal parts of an electric range be grounded. This is to protect people from electric shock in the event of a fault. Grounding provides a low resistance path for fault current to flow back to the source, which will cause the circuit breaker to trip. NEC Section 422.31 covers the disconnecting means for appliances. This section requires that a disconnecting means be provided for an electric range. The disconnecting means can be a circuit breaker or a switch. The disconnecting means must be readily accessible and must be capable of disconnecting the range from all ungrounded conductors. There are also specific requirements for the type of receptacle that is used to plug in an electric range. The receptacle must be of the proper voltage and amperage rating and must be of a grounding type. The receptacle must also be installed in a location that is readily accessible. In addition to the NEC, there may be local codes and regulations that apply to electrical wiring and equipment. It is important to check with the local authorities to determine what codes and regulations are in effect in a particular area. Electrical systems are designed with safety in mind, incorporating multiple layers of protection. The main breaker, as mentioned, serves as a primary safeguard, designed to trip and cut off power in the event of an overload or short circuit. This prevents overheating of wires, which can lead to fires, and protects against electrical shock. Individual circuit breakers provide a similar function for specific circuits within the home. Grounding is another critical safety feature. By providing a low resistance path for electricity to flow back to the source in the event of a fault, grounding helps to quickly trip the breaker, minimizing the risk of shock. Ground fault circuit interrupters or GFCIs are designed to detect even small imbalances in current flow, which can indicate a ground fault. GFCIs are commonly installed in bathrooms, kitchens, and outdoor areas where there is a higher risk of electric shock. Arc fault circuit interrupters or FCIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. FCIs are now required in many areas for circuits that serve bedrooms and other living areas. Regular inspections of electrical systems can help to identify potential problems before they become serious. Look for signs of damage to wiring, outlets, and appliances. If you notice any problems, have them corrected by a qualified electrician. When working with electricity, always follow safe practices. Turn off the power to the circuit before working on it. Use insulated tools and wear appropriate safety gear. If you are not comfortable working with electricity, hire a qualified electrician. Electricity is a powerful force that can be dangerous if not handled properly. By understanding the basics of electrical systems and following safe practices, you can protect yourself and your family from electrical hazards. Proper wiring is essential for electrical safety. Wires must be of the correct size for the amount of current they will carry. Wires must be properly insulated to prevent shorts and shocks. Wires must be properly connected to prevent loose connections, which can cause overheating and fires. Over time, electrical connections can loosen due to vibration, temperature changes, and other factors. Loose connections can cause a variety of problems, including flickering lights, malfunctioning appliances, and even fires. It is important to check electrical connections periodically and tighten them as needed. This is especially important for connections in electrical panels, which are subject to significant amounts of vibration and temperature change. When tightening electrical connections, be sure to use the correct torque. Over-tightening connections can damage the wires or terminals. Under-tightening connections can result in loose connections. If you are not comfortable tightening electrical connections, hire a qualified electrician. Surge protection is another important aspect of electrical safety. Power surges can damage electronic equipment. Surge protectors can help to protect electronic equipment from power surges. Surge protectors should be installed on all circuits that serve electronic equipment, such as computers, televisions, and stereos. There are two main types of surge protectors: point-of-view surge protectors and whole-house surge protectors. Point-of-view surge protectors are plugged into individual outlets and protect the equipment plugged into that outlet. Whole-house surge protectors are installed at the electrical panel and protect all of the equipment in the house. Backup power systems can provide power during a power outage. Backup power systems can be either battery-powered or generator-powered. Battery-powered backup power systems can provide power for a limited amount of time. Generator-powered backup power systems can provide power for a longer amount of time, but require fuel to operate. There are many factors to consider when choosing a backup power system, including the amount of power needed, the length of time power is needed, and the cost of the system. In addition to the technical aspects of electrical systems, there are also some important legal and regulatory considerations. Electrical work is typically regulated by state and local governments. Electricians are typically required to be licensed or certified. The electrical installations must typically be inspected to ensure that they meet code requirements. It is important to comply with all applicable legal and regulatory requirements when performing electrical work. Failure to do so can result in fines, penalties, and even criminal charges. Electrical safety is a shared responsibility. Homeowners, tenants, and electricians all have a role to play in ensuring that electrical systems are safe. By working together, we can prevent electrical accidents and injuries.